Right now, as you lie in the stillness of your room, you are moving. It is a strange thing to consider when the air around you is motionless and your breath is the only sound in the dark. But the reality is that everything you have ever known is currently rushing through space at 1.4 million miles per hour. In the time it took you to hear those last few words, you and the bed you are lying on have travelled over 600 miles through the void. You feel nothing. Your room remains quiet. The objects on your nightstand do not rattle. But this domestic stillness is a mask for a titanic, invisible velocity. This is not speculation. It is a measured, established fact of our existence. We are moving because we are caught in a current that began 13.8 billion years ago. A current so powerful that it is still carrying us and every galaxy we can see toward an unknown destination. But the most startling truth is not how fast you are moving. It is what you are breathing. As you inhale, you're drawing in the cooled down remnants of a fire that ignited at the very dawn of time. The oxygen and nitrogen molecules entering your lungs are the descendants of a primordial forge. You are sitting inside an echo. We often think of the beginning of the universe as a distant historical event that happened out there billions of years ago. But the data shows that the beginning is still happening right here, in the very space you occupy. To understand how this is possible, we have to look past what our eyes tell us. We see a room. We see the walls. We see the ceiling. But science has revealed that you are actually suspended in the centre of a gargantuan sphere of information. This is the observable universe, a sphere with a radius of 45 billion light years. Beyond that limit, light has not had enough time to reach us since the beginning of everything. Imagine for a moment that the universe is a vast, dark ocean. You are on a small boat in the middle of the night. You can only see as far as your lantern light reaches. That circle of light is your observable world, but you know the ocean continues far beyond the darkness. The edge you see is not a physical wall, it is an edge in time. When we look out into the furthest reaches of space, we are not just looking across distance, we are looking into the past. We are looking at the history of the world until there is simply no history left to see. If you find wonder in these invisible mysteries, subscribe now. The investigation into our true origin begins here. In most stories of our beginning, we are told of an explosion, the Big Bang. But the term is misleading. There was no sound in the way we understand it, and there was no outside for the universe to explode into. Instead, there was a sudden, violent stretching of space itself. But before there was matter, and before there was even light, there may have been something more fundamental: information. There is a growing idea in modern physics that the universe did not begin as a pile of stuff, but as a calculation. Imagine a drop of red ink falling into a glass of clear water. You watch the ink spread, curling into clouds of crimson, until the entire glass is a uniform pink. You have never seen, and will never see, that pink water spontaneously separate back into a single red drop. This is the arrow of time, the rule that states things move from order to disorder, from a concentrated beginning to a diluted future. But this arrow is not a law of iron, it is a matter of probability. If you had an infinite amount of time, a 1 followed by 100 sextillion zeros of years, by pure random chance, those ink molecules would eventually bump into each other in just the right way to form a red drop again. They could even, with enough time, form the shape of a human brain. This leads us to a haunting possibility that competitor documentaries often ignore: the information genesis. If our universe is 13.8 billion years old, it is currently in its living phase, a glass of water where the ink is still actively doing interesting things. But what if the Big Bang was not the absolute start? What if we are actually a pop-up universe, a spontaneous fluctuation of information that emerged by pure chance in a much older, dead universe? In this view, everything you see around you is not a journey from a beginning to an end, but a brief, improbable dream of a cosmos that has already finished its story. This is why we must look at the auditory beginning. While most people focus on the flash of light, the early universe was actually a medium for sound. Before the first stars formed, the cosmos was filled with a hot, thick plasma, a primordial soup that was dense enough to carry vibrations. Imagine raindrops hitting a still pond. Each drop creates concentric ripples that move outward, pushing and pulling at the water. In the early universe, gravity was pulling matter in, while the intense heat of light was pushing it back out. This tug of war created the baryon acoustic oscillations, the first song of the universe. These were not just random noises, they were physical ripples of pressure that moved through the fabric of everything. When the universe finally cooled enough for atoms to form, these sound waves were suddenly frozen in place. They became a standard ruler for the cosmos. The positions of the galaxies you see in the sky tonight are not random. They are the crests of those ancient sound waves, locked into the geometry of space forever. You are sitting in the middle of that symphony. The very structure of the world you inhabit is a high-resolution map of a sound that played out in the first moments of time. But as we peel back these layers, the motion, the fire, the sound, and the information, we eventually hit a wall. It is a boundary where the very rules of our reality stop making sense. Scientists call it the Planck era. It is a moment so close to the beginning that our entire observable universe, with its 200 billion galaxies, was compacted into a space smaller than a single grain of salt. At this scale, the laws of gravity and the laws of the tiny quantum world were locked in a room together and simply could not agree on how to behave. This is the complication that haunts every physicist. You see, to understand how the universe really began, we have to understand what happens when space and time themselves start to break apart. We are searching for the north of the North Pole. We are looking for the moment when nothing became everything. And as you lie here, moving at over 1 million miles per hour through the remnants of that first fire, you are the latest chapter in that 14 billion-year-old investigation. The beginning is not behind us. It is the very fabric of the now. And for tonight, as we prepare to move beyond the Planck wall, that is enough. We often imagine the universe as a giant dark room, a vast empty container that was already there, waiting for the light to be switched on. In this mental model, space is the stage and time is the ticking clock on the wall, both existing independently of the play being performed. But the data tells us something far more unsettling. Space and time are not just things we live in. They are properties that were born. They are not the stage. They are the actors themselves. To understand this, we must first look at the walls of our vision. When you look up at the night sky, you are not seeing the universe as it is now. You are seeing an edge in time. Light is the fastest thing in existence, yet it is also a prisoner of its own speed. Because the universe is 13.8 billion years old, we can only see the parts of the cosmos whose light has had enough time to reach us since the beginning. Imagine you are standing in the centre of a vast silent forest at night. You hold a lantern that can only cast its glow a few yards in every direction. Beyond that circle of light, the forest might go on for miles, or it might end abruptly. But for you, the edge of the world is defined by where the light fades into the black. You are suspended in the centre of a gargantuan sphere of information. This is the observable universe. This sphere has a radius of roughly 45 billion light-years. Within this bubble of visibility, there are around 200 billion galaxies. each containing hundreds of billions of stars. This is not speculation. These are numbers mapped and measured by our most sensitive instruments. But as we peer toward the edge of this sphere, we encounter a boundary, not a wall of stone, but a wall of time. We are looking at the past until there is simply no past left to see. It is here that the human mind begins to stumble. We naturally ask, what is beyond that edge? What was there before the light began to travel? The famed cosmologist Stephen Hawking offered an answer that is as elegant as it is difficult to grasp. He suggested that searching for a time before the beginning is as meaningless as searching for a point north of the North Pole. Just as the surface of the Earth is a curved geometry that rounds off at its peak, the geometry of space-time may have rounded off at its origin. At the North Pole, the very concept of north ceases to exist because all directions lead south. Similarly, at the moment of the beginning, the very concept of before may cease to exist because time itself was only just beginning to unfold. If you find wonder in these invisible mysteries, subscribe now. The investigation into our origin begins here. To truly comprehend this limit of north, we have to scale our perspective. In the previous chapter, we noted that you are currently moving at 1.4 million miles per hour. In the few minutes you have been listening to these words, you have travelled thousands of miles through the void. Yet your room remains still. This stillness is the greatest illusion of our lives. The 17th century scientist Galileo understood this through a domestic analogy. The sailor in a windowless cabin. He imagined a ship moving smoothly across a glassy sea. Inside the cabin, a goldfish swims happily in its bowl. A dropped plate falls straight to the floor. Butterflies flutter about the room. To the sailor, it feels as if the ship is still in port. There is no experiment he can perform within those four walls to prove he is moving. You are that sailor. Your room is that cabin. The Earth, the Sun, and the entire Milky Way are the ship carrying you through a sea of space-time that is itself growing and stretching. But unlike the sailor's ship, which has a destination, our ship is space itself. And space does not just exist in a void, it is the void. This brings us to the physics hack of the beginning. If the universe is all there is, how can it have an edge? If there is an edge, there must be something outside of it. But if there is something outside, then the universe wasn't all there is to begin with. Scientists resolve this paradox by considering the universe as a hypersphere. Think of a tiny ant crawling on the surface of an orange. The ant can only see a small patch of skin at a time, just as you can only see a small chunk of the universe. To the ant, the orange seems to go on forever in every direction. But if that ant starts walking in a perfectly straight line, it will never find a wall. It will never fall off an edge. Instead, it will eventually find itself back exactly where it started. The surface of the orange is finite. It has a limited amount of skin, but it has no border. Our 3D space may be exactly like that peel. If you were aboard a spaceship flying in a straight line for long enough, you might not find the end of the world. You might simply find the back of your own head. This is what we mean when we say space is curved. It is the most mind-bending thing in the universe. Mass and energy bend the very fabric of reality. This bending is not just a poetic metaphor. It is a measured physical tension in the fabric of existence. This curvature leads us to a deeper investigation of our own history. If we follow the ant on its journey back through time, we see the orange shrinking. The further back we go, the smaller and more curved the universe becomes. We eventually reach a point where our entire observable world, all 200 billion galaxies, is compressed into a space smaller than a single proton. At this scale, the very idea of distance and duration begins to flicker like a dying candle, the continuous and coherent space-time you are familiar with, the space that allows you to reach for a glass of water, the time that allows you to wait for a breath, is replaced by an unpredictable, varying foam-like texture. In this quantum foam, the rules of cause and effect simply stop applying. Microscopic black holes and wormholes pop into existence and vanish without a trace, and for a brief energetic moment, anything goes. This is the Planck era. It is the ultimate limit of what we can understand with our current science. We are not searching for an explosion that happened in space. We are searching for the origin of the stretching that created space itself. The Big Bang was not the beginning of a fire. It was the birth of the geometry that allowed the fire to exist. When we ask, how did the universe really begin? We are actually asking, how did the relationship between things begin? Space and time may simply be emergent phenomena, the collective feeling of billions of tiny quantum relationships. Imagine you are looking at a beach from a great distance. It looks like a smooth, continuous yellow ribbon. But as you get closer, you realize the ribbon is actually composed of trillions of individual grains of sand. There is no beach between the grains. There are only the grains themselves and their relationships to one another. You are a collection of world lines. You are a bundle of paths through these 4 dimensions. Before you were born, the threads of matter that make you up were dispersed across the stars. For a fleeting moment, those threads have knotted themselves together to form the person listening to this, and eventually those threads will scatter again. We often ask what the universe is made of, but we rarely ask what you are made of in the eyes of the cosmos. You are a 14-billion-year-old experiment in self-awareness. You are the universe's way of looking back at itself and asking, where did I come from? As we lie here in the dark, moving through a current of time that we did not choose, we are approaching the Planck wall. We are moving toward a moment where nothing and everything were the same thing. To move beyond this point, we have to abandon the idea of a simple, linear history. We have to accept that the beginning is not just a point in the past, but a boundary that defines every second of your current existence. In the next chapter, we will attempt to breach that wall. We will look at the first trillionth of a second, a moment so brief that it makes a blink of an eye seem like an eternity, to see how the grain of salt became the sky. But for now, consider the scale of your own vision. You are not a spectator watching a documentary. You are a participant in a 45 billion light-year sphere of ancient moving light. You are the sailor in the cabin, and the ship is finally heading out into the deep. The North Pole is behind us. The investigation continues. And for tonight, as the stillness of your room masks the titanic velocity of your journey, that is enough. To understand the absolute beginning, we must first travel back through the history of our understanding, specifically to the turn of the 20th century and a German theoretical physicist named Max Planck. Before Planck, science largely viewed the universe as a smooth, continuous stage, a place where energy flowed like water and distances could be divided infinitely. But Planck discovered something that would forever change our perception of reality. The universe has a resolution. It is not a smooth stream, but is instead composed of discrete chunks or quanta. This realization led to the quantization of light into photons, but more importantly, it allowed Planck to define the absolute floor of existence. Using universal constants like the speed of light and the force of gravity, he calculated a set of units that mark the boundary where our current laws of physics simply stop working. This boundary is what we call the Planck era, and it is the closest we can ever get to the moment of creation using the tools of modern science. To visualize the scale of the Planck era, imagine the entire observable universe, every galaxy, every star, every planet and every person who has ever lived, compressed into a volume so small that it is beyond human comprehension, at a time of roughly 100 million trillion trillionths of a second after the beginning, all of this was smaller than a single grain of salt. Consider that grain of salt for a moment. If you were to hold one in the palm of your hand, it would feel weightless, almost insignificant. Yet, 13.8 billion years ago, that tiny speck contained the potential for every sun that will ever ignite and every black hole that will ever consume a star. This is the ultimate backstory of your existence. You were once part of a density so extreme that the very fabric of space was essentially a single vibrating point. Planck's calculations give us 3 specific limits that define this era: the Planck length, the Planck time, and the Planck temperature. The Planck length is the smallest possible measurement of distance, roughly 1.6 times 10 to the power of minus 35 meters. To put this in a domestic perspective, this length is about 100 quintillion times smaller than a single proton. If a proton were scaled up to the size of the entire observable universe, a Planck length would still be only about the width of a human hair. It is the pixel size of our reality. The Planck time is the duration it takes for light to travel across that minuscule distance, a mere 5.39 times 10 to the power of minus 44 seconds. This is a fraction of time so small that a billion years, by comparison, would seem like the blink of an eye. During the Planck era, the universe was only a single unit of Planck time old. Finally, there is the Planck temperature, often called absolute hot. This is the highest temperature possible before particles are torn apart by their own energy. It sits at approximately 1.4 times 10 to the power of 32 Kelvin. For context, the core of our Sun burns at a mere 15 million degrees Celsius. Even the most violent phenomena we can witness, such as a supernova explosion, reach only about 100 billion degrees. Even the Large Hadron Collider in Switzerland, which smashes atoms together at near-light speeds, has only managed to briefly produce 5.5 trillion degrees, 50 times hotter than a supernova, but still an absolute zero compared to the blistering heat of the Planck era. At this scale, the universe was not just hot and small, it was lawless. Today, everything we experience is governed by 4 major forces: the strong force that holds atoms together, the weak force governing radioactivity, the electromagnetic force that gives us light and electricity, and gravity. But in the Planck era, these forces did not exist as separate entities. They were likely unified into a single superforce that we do not yet have the mathematics to fully describe. This creates a massive complication for science. Our best theory for the very large is Einstein's general relativity, which treats space and time as a smooth, curving fabric. Our best theory for the very small is quantum mechanics, which describes a world of probability and discrete jumps. Usually, these 2 theories live in separate neighbourhoods and never have to interact. But in the Planck era, the entire large universe was forced into the tiny quantum scale. When you try to combine the 2 theories at this density, the math breaks down and produces nonsense results. It is like trying to play a game of chess, where the board is also a player, constantly changing its own squares while you try to move your pieces. This Planck wall is a barrier to our sight. Because light itself is quantized and cannot have a wavelength smaller than the Planck diameter, we cannot see anything that happened before this moment. We are like people standing outside a house with frosted windows. We can hear the muffled sounds of the party inside, the echoes of the beginning, but we cannot see the faces of the guests or the layout of the room. What we do know is that this tiny salt-grain universe was incredibly smooth. Despite the chaotic quantum energy, the temperature in one corner of that tiny speck was remarkably similar to the temperature in another. This homogeneity is one of the greatest mysteries of our origin. It implies that everything was once in thermal contact. Essentially, that the entire universe was once a single unified thought before it was flung apart. As you rest tonight, it is worth reflecting on the fact that your own body is composed of approximately 7 octillion atoms. Each one of those atoms contains quarks and electrons, whose history can be traced back through 13.8 billion years of expansion, cooling and star formation, all the way back to that single grain of salt. You are the result of a process that has never been broken. But to understand how that grain of salt became the vast sky you see out your window, we have to look at what happens when the frosted glass of the Planck wall begins to crack. We have to enter the world of the quantum foam, where space and time are not a stage, but a bubbling, unpredictable ocean. The investigation into the very first fraction of a second is not just a search for facts, it is a search for the limit of what can be known. We are standing at the edge of the Planck wall, looking back at a moment when nothing and everything occupied the same tiny space. In the next chapter, we will see what happens when the rules of our world finally begin to take shape. We will witness the first time the universe chose its identity. But for now, as you consider the impossible density of your own origin, that is enough. In the previous chapters, we reached a boundary called the Planck Wall, a place where the history of our universe becomes a muffled echo behind frosted glass. But to truly understand how the universe began, we have to look at what happens when our understanding of reality simply stops working. We have to address the complication. At the very beginning, 13.8 billion years ago, the rules of our world did not just bend, they broke. In our daily lives, we are used to a universe that follows predictable laws. If you drop a spoon, it falls to the floor. If you watch a clock, the seconds tick by with rhythmic, unswerving precision. We have spent centuries codifying these observations into the language of mathematics, and for the most part it works perfectly. But as we approach the first trillionth of a second, we find that the two pillars of modern science, general relativity and quantum mechanics, are fundamentally incompatible. To visualize this, imagine these two theories are like two brilliant but stubborn architects who have been locked in a room together and tasked with designing the same building. They simply cannot agree on how the universe should behave. The first architect, Albert Einstein, represents general relativity. His vision is one of grand, smooth curves. To him, space and time are like a seamless fabric that stretches and warps under the weight of stars and galaxies. It is a world of absolutes, where every movement is part of a continuous, flowing geometry. The second architect represents quantum mechanics, the study of the incredibly small. This architect sees the world not as a smooth fabric, but as a collection of discrete, jittery chunks or quanta. In this view, nothing is certain. Particles don't have definite locations. They have probabilities of being in multiple places at once. It is a world of pixelated reality, where the very act of looking at something changes how it behaves. Usually these two architects never have to speak to each other. General relativity handles the large, the orbits of planets and the expansion of space, while quantum mechanics handles the tiny, the behaviour of atoms and subatomic particles. They live in separate neighbourhoods and operate under separate rules. But in the Planck era, the entire large universe was forced into the tiny quantum scale. The two architects were forced to share the same blueprints for a space-time that was smaller than a single proton. When you try to combine these two sets of rules at this extreme density, the math produces nonsense results. It is like trying to play a game of chess where the board is also a player, constantly changing the shape and size of its own squares while you are trying to move your pieces. In this environment, the very concept of up, down, or then starts to lose its meaning. In the 1950s, the physicist John Archibald Wheeler gave us a name for this lawless state, the quantum foam. He realised that if you could zoom in far enough, past the level of atoms, past the level of protons, all the way down to the Planck length, you would see that space-time is not a smooth, empty stage. Instead, it is a bubbling, dynamic, and violent ocean of energy. Think of space at this scale like the surface of a carbonated drink. From a distance, the liquid looks still and transparent. But as you look closer, you see a frenzy of activity. Bubbles are constantly popping into existence and then vanishing just as quickly. In the early universe, these bubbles were not filled with air. They were microscopic black holes and wormholes. This is difficult to grasp because it challenges our intuition about what nothing is. We think of a vacuum as empty, but the quantum foam tells us that even empty space is teeming with virtual particles that appear and disappear in the blink of a Planck time unit. Because of Heisenberg's uncertainty principle, we cannot precisely define the energy or the geometry of a single point within this foam. For the briefest of moments, anything goes. In this chaotic environment, space and time were not yet the reliable dimensions we know today. They were an unpredictable, varying texture that shifted randomly. Imagine trying to walk across a floor that is constantly turning into liquid and then back into solid, while the walls around you expand and contract without warning. This is the universe in its most primal state, a lawless maelstrom, where the four fundamental forces were likely unified into a single superforce we still don't fully understand. This lawlessness is why the beginning is so hard to map. In our modern world, gravity is predictable. It keeps you pinned to your chair and holds the Earth in orbit around the Sun. But in the quantum foam, gravity was forced to behave like a quantum particle. Some scientists believe this means gravity is communicated by its own messenger, a particle called a graviton, though it is so weak that it has remained invisible to our instruments. Others believe that space-time itself is pixelated into tiny loops or lines, a theory known as loop quantum gravity. Regardless of which theory eventually wins, the reality of the quantum foam remains the same. At the very heart of everything you see, there is a fundamental shimmer. The smooth reality of your room tonight, the solid feel of your bed, the steady rhythm of your breathing, is actually the result of trillions upon trillions of these quantum fluctuations averaging out into something stable. You are made of this foam. Every atom in your body is built upon this foundation of micro black holes and wormholes that popped in and out of existence 13.8 billion years ago. You are the calm surface of a very deep and very turbulent ocean. This brings us to a startling realization. If the beginning was this lawless and chaotic, how did it ever become the organized, flat, and structured universe we see today? If you have a bubbling foam of energy, you would expect it to grow into a messy, uneven clump of matter. Yet, when we look at the oldest light in the sky, we see that the early universe was remarkably smooth and uniform. This is the next layer of the mystery. The complication of the quantum foam leads directly into the deeper layer of our investigation. Something had to happen to take those tiny, chaotic bubbles and stretch them out so quickly that the chaos was ironed flat. Something had to turn the lawless foam into a coherent sky. As we move beyond the first fraction of a second, we encounter the most violent and transformative event in the history of the cosmos. It is a moment where the grain of salt didn't just grow. It exploded in a way that defies every intuition we have about speed and scale. But for now, as you lie in the stillness of the now, consider that beneath the silence of your room, the fabric of space is still vibrating with the remnants of that ancient, bubbling foam. The North Pole of our history was not a point of stillness, but a point of ultimate lawless energy. We are the survivors of that chaos. The architects are still in the room, and they are still arguing. But as the universe began to cool and grow, one of them was about to take control of the blueprints and change everything. And for tonight, as we prepare to witness the moment the foam became the stars, that is enough. Right now, as you lie still, the distance between you and the furthest galaxies in the sky is increasing. Space is not a static floor, it is growing. But the bang that started this growth was not an explosion that happened in space. It was a sudden, violent stretching of space itself. We have been taught to call it the Big Bang, but for the first trillionth of a second there was no sound. There was only a silence so energetic that it changed the geometry of existence forever. This is not speculation. It is a model known as cosmic inflation, first proposed by theoretical physicist Alan Guth in 1979 to solve the broken parts of the Big Bang theory. To understand how the universe we see tonight became so vast and yet so remarkably smooth, we must look at a moment that lasted less than a trillionth of a second. In that flickering instant, the universe did not just grow, it doubled in size at least 90 times. It is no fair reflection on your brain to say that these numbers are beyond true human comprehension. We are evolutionarily attuned to scales that are relevant to us. The length of a day, the distance of a walk, the weight of a stone. When we hear that the universe doubled 90 times in a fraction of a second, the number 90 feels manageable, while the reality is astronomical. To understand this scale, we must translate it into a domestic reality you can touch. Imagine you are holding a single gigantic sheet of paper. It is standard paper, only about 1/10 of a millimetre thick. If you fold that paper in half once, it becomes 2/10 of a millimetre. Fold it again, and it is just under half a millimetre. By the third fold, it is the thickness of your fingernail. So far, this is unremarkable. But exponential growth is a deceptive force. By the time you reach 7 folds, that single sheet of paper has reached the thickness of an entire notebook. At 10 folds, the paper is now as thick as your hand is wide. The world record for actually folding a piece of paper sits at just 12 folds. But if you could continue, if you had the strength and the reach to keep going, the numbers would quickly escape the room. At 23 folds, your pile of paper would be 1 kilometre thick. At 30 folds, the paper would be 100 kilometres high, officially reaching outer space. As you continue to fold, the scale begins to dwarf the world you know. At 42 folds, the paper would reach the moon. At 51 folds, it would reach the sun. By the time you reach 81 folds, that single piece of paper would be as wide as the Andromeda galaxy, 141,000 light-years across. And finally, at 90 folds, the same number of doublings the universe experienced in its first instant, that single sheet of paper would be larger than the entire Virgo supercluster, a gargantuan collection of galaxies spanning 13 million light-years across the void. This is the deeper layer of our beginning. The universe did not grow like a tree. It grew like a thought that encompasses everything at once. This sudden inflation blew the universe up to more than an octillion times its original size. It took the tiny bubbling chaos of the quantum foam we discussed in the last chapter and stretched it so violently that the bubbles were ironed flat. This is why when you look out at the horizon of the sea, the world appears flat to your eyes. And it is a matter of perspective. From the shore, the ocean seems to be a straight line because you are seeing only a tiny fraction of a much larger curved sphere. Inflation did the same to the cosmos. It took a curved, complicated beginning and expanded it so much that our local patch, the entire observable universe, now appears perfectly flat to our most sensitive instruments. This is what scientists call the flatness problem, and inflation is the elegant physics hack that solves it. But inflation did something else, something even more vital for your existence tonight. Before this moment, at the subatomic scale, the universe was filled with tiny random quantum fluctuations, minuscule shimmers of energy where one spot was slightly denser than the spot next to it. Usually these shimmers are too small to ever matter, but inflation acted like a gargantuan magnifying glass. In less than a trillionth of a second, those subatomic shimmers were instantly scaled up to a cosmic size. The tiny points of overdensity in the quantum foam became the seeds for every structure in the modern world. They became the nurseries for the first stars, the gravitational anchors for galaxies, and eventually the very atoms that make up your body. You are a 13.8 billion-year-old quantum shimmer, stretched across the sky by a force we still don't fully understand. Scientists are still searching for the why behind this event. They theorize that a new kind of energy field, called the inflaton field, drove this exponential expansion. When this field finally decayed, it poured its remaining energy back into the universe in a phase known as reheating. This was the decisive creation of matter. The cold, empty, inflated void was suddenly flooded with a hot, dense plasma, the primordial soup from which everything you have ever loved was cooked. This reheating marks the end of the grand unification epoch. It is the moment the penny dropped, and the laws of nature began to choose their identities. The universe was finally roomy enough for the forces we know, gravity, electromagnetism, and the nuclear forces, to begin their long work of building a world. As you lie here, consider that the very space in your room was once part of that violent, silent stretching. The bang was not a noise you could have heard, but a transformation you can still feel in the very geometry of the night sky. The universe is still beginning. Space is still growing between the stars. And the fact that everything seems so organized, so flat, and so consistent is the direct legacy of those 90 doublings that took place before the first second of time had even finished its first tick. The grain of salt has become the Virgo supercluster. The paper has been folded. And for tonight, as you drift in the expanded quiet of a cosmos that is still finding its limits, that is enough. We often think of the Big Bang as a flash of blinding light, a silent explosion that filled the void with radiance. But for the first few 100,000 years of our history, the universe was dark. It was not empty, but it was opaque. It was filled with a hot, thick, and roiling plasma, a primordial soup so dense that light itself was a prisoner. Imagine you are standing in a thick, golden fog. You hold a powerful lantern in your hand, but the light cannot travel. The individual photons, the particles of light, are constantly bumping into a dense swarm of electrons and protons. They are trapped in a subatomic maze, scattering in every direction, unable to find a clear path. To an outside observer, if one could have existed, the universe would have looked like a dark, glowing ember, radiating heat but revealing no shapes. But while light was trapped, sound was free to roam. This is the sensory layer of our beginning that is so often forgotten. Before the first stars ignited, before the first galaxies were born, the universe was a medium for a titanic rhythmic vibration. It was a symphony played on the fabric of space itself. This is not a poetic metaphor. It is a measured physical reality known to cosmologists as baryon acoustic oscillations. To understand how this sound was born, we must look at the tug of war that was taking place inside that hot primordial soup. In your room tonight, you are surrounded by baryons, the technical name for the normal matter that makes up your bed, your breath, and your body. In the early universe, this matter was being pulled in two opposite directions. First, there was gravity. Gravity is the patient builder of the cosmos. In the early universe, certain patches of the primordial soup were slightly denser than others, small clumps of matter that had been seeded by the quantum shimmers we discussed in the previous chapters. Gravity acted on these clumps, pulling more matter toward the centre, trying to collapse everything into a single, tight point. But as the matter was squeezed together, it became incredibly hot. And as it became hot, the photons, those trapped particles of light, pushed back. This is the repulsive force of radiation pressure. The more gravity tried to pull the matter in, the harder the light pushed it back out. This cycle of squeezing and pushing created a vibration. It was a rhythmic pulse that moved through the entire universe. As the light pushed the matter outward, it created concentric ripples. Imagine a still pond on a rainy night. Every time a raindrop hits the surface, it creates a perfect expanding circle. The ripple pushes the water outward in a wave of pressure. Now imagine 1 billion raindrops hitting that pond simultaneously. The ripples overlap, they interfere with one another, and they create a complex, beautiful pattern of peaks and valleys across the surface. You are sitting in the middle of that pond. 13.8 billion years ago, the entire observable universe was vibrating with these ripples. The song of the universe was not a melody you could have heard with your ears. The frequencies were far too low, with wavelengths spanning hundreds of thousands of light years, but it was a physical movement of matter. This song lasted for 380,000 years. It was the heartbeat of the young cosmos. But then, something transformative happened. As the universe continued to expand, it began to cool. When the temperature finally dropped to around 3000 Kelvin, roughly half the temperature of the surface of our Sun, the electrons that had been roaming freely were finally moving slowly enough to be captured by the atomic nuclei. This is the moment of recombination. In a cosmic instant, the golden fog cleared. The electrons were no longer scattering the light. The photons, which had been trapped in their maze for 380,000 years, suddenly found their paths clear. They escaped, travelling in straight lines across the void. This was the first light, the birth of the cosmic microwave background that scientists first detected as a faint radio hiss in 1964. But when the light escaped, the sound stopped. The photons were the force that had been pushing the matter outward, keeping the ripples moving. Without that outward pressure, the ripples were frozen in place. The concentric circles of matter, the baryon acoustic oscillations, could no longer expand. They were locked into the geometry of space exactly as they were at the moment the fog cleared. This is the standard ruler of the cosmos. When we look out at the sky tonight, the positions of the galaxies are not random. They are the crests of those ancient sound waves. Scientists have measured the distances between hundreds of thousands of galaxies and found a startling pattern. There is a slight statistical preference for galaxies to be separated by a distance of 500 million light-years. This distance, 150 megaparsecs, is the radius of that first sound wave, stretched out by 13.8 billion years of expansion. It is the scale of the first song, written into the very map of the universe you see from your window. Consider what this means for your own history. The matter that eventually formed the Milky Way, the Sun, and the atoms in your own body was once part of that rhythmic vibration. You are the result of a specific peak in the sound of the beginning. You are sitting inside a frozen symphony. This is not speculation. This is measured reality. Multiple independent teams of astronomers have confirmed these oscillations by studying the distribution of galaxies across the deepest reaches of space. We can hear the beginning by looking at where the stars are. But as we rest in the quiet of the now, we must face a deeper complication. While the sound waves were building the large-scale structure of the world, another, more invisible force was at work. We know that normal matter, the baryons that carried those sound waves, makes up only 5% of the universe. Something else was acting as a template, an invisible hand that pulled the first atoms together into the nurseries of the first stars. To understand how the song became the stars, we have to look into the dark. In the next chapter, we will look at the final separation of the forces, the moment when the universe finally chose its identity and allowed the first light to move through the void. We will witness the identity crisis that defined the rules of our reality. But for now, listen to the silence of your room. It is a quiet that was earned through hundreds of thousands of years of vibration. The echo of that first song is still here, in every breath you take and every star you see. The universe is not a random collection of things. It is a high-resolution map of a sound that played out when time was young. The song has ended, but the music is still playing. And for tonight, as you drift in the remnants of that primordial symphony, that is enough. In the previous chapters, we witnessed the sudden, violent stretching of space during inflation, and heard the first frozen symphony of the young cosmos. We saw how the tiny bubbling chaos of the quantum foam was ironed flat, creating the vast and smooth stage on which the stars would eventually appear. But as we rest in the quiet of the now, we must face a deeper complication. The rules of our reality were not always as they are tonight. Everything you experience in your room right now is governed by 4 fundamental forces of nature. These are the invisible laws that dictate how every atom in your body behaves, how the light reaches your eyes, and why your feet remain planted on the floor. To understand how the universe really began, we have to look back to a time when these 4 forces were not separate entities, but were unified into a single, faceless power. This is the story of the Grand Unification Epoch, a moment of extreme identity crisis that defined the very blueprints of existence. To visualize this, first consider the world you know. Imagine reaching for your television remote. As you press a button, several laws of nature spring into action simultaneously. Gravity is the first. It is the patient builder that keeps you pinned firmly to your seat and holds the Earth's atmosphere close to the surface so that you can breathe. Yet, despite its cosmic reach, gravity is remarkably weak. You can overcome the gravitational pull of the entire Earth with the muscles of a single arm just to lift that remote. As the remote clicks, an invisible beam of infrared light, electromagnetic radiation, travels across the room. This force is responsible for light, electricity, and the magnetic fields that power our modern world. Inside the television and inside your own eyes, atoms are held together by this same force. But if we peer deeper into the very heart of those atoms, we find the final 2 forces, the strong nuclear force and the weak nuclear force. The strong force is the cosmic glue. It binds protons and neutrons together in the centre of every atom, and it holds together the even smaller particles called quarks that make up those protons. Without the strong force, you would instantly dissolve into a cloud of subatomic dust. Finally, the weak force is the agent of transformation. It governs the radioactive decay of particles and drives the nuclear fusion at the core of our Sun, providing the heat that makes life possible. These 4 forces, gravity, electromagnetism, and the 2 nuclear forces, act together to shape every second of your life. But 13.8 billion years ago, During the first trillionth of a second, the universe was far too energetic for these forces to maintain their separate identities. This is where we encounter the identity crisis. This is confirmed science, not speculation. Scientists use an elegant analogy to explain how these forces split apart. The spinning coin. Imagine you are sitting at a table with a single coin. You flick your wrist and send it spinning across the wood. While the coin is spinning, it is imbued with energy. It moves so fast that the distinct faces of heads and tails blur together. In that state, the coin has a single unified identity. It is a flickering silver orb that is both heads and tails simultaneously. You cannot distinguish between the two faces because the energy of the spin has erased their differences. The early universe was exactly like that spinning coin. At the impossibly high temperatures of the beginning, the fundamental forces were spinning with such extreme energy that their individual properties blurred into one another. As we look back toward the start, we see the weak nuclear force and the electromagnetic force merge into a single faceless power known as the electroweak force. If we increase the energy even further, the spinning coin concept applies again. At even higher temperatures, the strong force blurs into the electroweak, creating a single unified whole, the electro-strong force. This ultimate unification is what defines the Grand Unification epoch. This period began just after the Planck era, which we explored in earlier chapters. Despite the universe expanding rapidly, it is testament to just how dense everything started that even during this epoch, the entire observable cosmos, everything you will ever see, was still smaller than a single quark. Consider the scale of that statement for a moment. All 200 billion galaxies were compacted into a space trillions of times smaller than a single proton. In this hyper-dense environment, the temperature reached 100,000 trillion Kelvin. This is a number that sits 1 trillion times higher than the Large Hadron Collider in Switzerland has ever managed to produce. At these blistering heats, the laws of nature as we know them simply did not exist. The universe was a free-for-all of energy and matter, filled with particles undergoing an extreme identity crisis. In this post-inflationary maelstrom, photons transform spontaneously into matter and antimatter pairs. Quarks shifted into leptons, and leptons into quarks. Because the forces were unified, there was no stability. There was only a chaotic, energetic soup, where everything was in a constant state of becoming something else. But then, the energy began to fade. The spin of the coin started to slow down. As the universe expanded and cooled, it underwent a series of phase changes. This is the second analogy we must use to understand the beginning: water freezing into ice. When water is a vapour, its molecules move with high energy in random directions. It is highly symmetrical and uniform. But as you drop the temperature, the vapour becomes a liquid. And then finally, it crystallizes into solid ice. At each transition, the properties of the water change fundamentally, and the original symmetry is lost. The universe followed this exact pattern of symmetry breaking. Approximately 1 trillionth of a second after it began, the temperature dropped to a mere 1,000 trillion degrees. This was cool enough for the first great split to occur. The penny dropped. The strong nuclear force broke free from the unified electro-strong force. Just like the spinning coin eventually loses its energy and settles onto the table, the universe chose a face. The forces that were once a single unified orb crystallized into separate entities. This event was catastrophic and transformative. It ended the perfect symmetry of the early universe and began the process of building the world we recognize as our own. But there is a catch. This identity crisis created a universe that was potentially broken from the start. When we compare these starting conditions with the result we see tonight, the numbers don't quite add up. This is what scientists call the horizon problem and the flatness problem. If the universe was simply a chaotic explosion of forces splitting apart, we would expect to see a messy, uneven cosmos. We would expect to see massive variations in temperature from one side of the sky to the other. Yet, when we measure the temperature of empty space tonight, we find that it is remarkably similar in every direction, approximately 2.7 Kelvin. How could 2 points on opposite sides of the universe, separated by 93 billion light years, have averaged out their temperatures without information travelling faster than the speed of light? This is the deeper layer of the complication. The final separation of the forces was not a smooth process. It was a series of energy drops that left pinches and pockmarks in the fabric of space-time. These imperfections should have led to a curved, distorted universe. But as we noted in our chapter on inflation, our most sensitive instruments show that the universe is perfectly flat. It is like tossing a coin and having it land perfectly on its edge. The probability of this happening by chance is so small that it suggests something else was at work, a fine-tuning of the initial conditions that allowed for the variety and diversity we see today. As you lie here, consider that your own body is the beneficiary of this identity crisis. During the grand unification epoch, you were merely a potential within a unified force. But as the forces split, as the coin settled and the water froze, the rules were established that allowed mass to exist. In the next chapter, we will look at what happens when these forces finally begin to govern matter. We will witness the war of matter, a ruthless particulate battle where the winner was decided by a tiny, lucky imbalance. The only reason you are here to listen to this tonight. But for now, listen to the stillness of your room. It is a stillness defined by four forces that have been separated for nearly 14 billion years. Booking, the identity crisis of the beginning is over, and the rules are set. The universe has chosen its face, and for tonight, that is enough. Imagine for a moment that you have a perfect twin. This twin is identical to you in every way. The same height, the same memories, the same quiet rhythm of breathing, except for one fundamental, terrifying difference. Every electrical charge in their body is reversed. Where your atoms have a negative electron, theirs have a positive one. Where you have a positive proton, they have a negative one. In the language of physics, this twin is made of antimatter. If you were to reach out and touch the hand of this twin, there would be no brotherly embrace. Instead, the moment your skin met theirs, both of you would vanish in a flash of light more powerful than any nuclear explosion. This is not a plot from a science fiction novel. It is the measured reality of our standard model. And 13.8 billion years ago, during the first second of existence, the universe was filled with trillions of these twins, locked in a ruthless, particulate battle for the right to exist. In your room tonight, you are surrounded by the victors of that battle. Every object you can touch, the fabric of your sheets, the glass of water on your table, the very marrow in your bones, is the leftover of a cosmic war that almost resulted in a universe made of nothing but dead, flickering light. To understand how you came to be the winner, we have to look at the blueprints of matter. Our current understanding of the world is built on the standard model of particle physics. This is not speculation. It is the most successful physical theory in human history, verified by decades of experiments in massive particle colliders. The model tells us that there are 12 fundamental, unsplittable building blocks of matter, including the quarks that make up your protons and the leptons, like electrons, that orbit them. But the model also contains a haunting symmetry. In 1928, the physicist Paul Dirac realized that the laws of nature required every particle of matter to have an antimatter counterpart. These particles are real. We produce them in labs today. We see them in the radioactive decay of a banana on your kitchen counter, which produces a single positron, an anti-electron, roughly every 75 minutes. In the beginning, during the first billionth of a second, the universe was so hot and energetic that matter and antimatter were being born in pairs directly out of pure energy. For every electron that popped into existence, a positron appeared with it. They were created in perfect balance, and in such a dense, frantic environment, they didn't last long. As soon as they met, they annihilated, transforming back into the photonic shrapnel of pure radiation. Based on everything we know about the laws of physics, this should have been the end of the story. Matter and antimatter should have continued this cycle of creation and destruction until the universe cooled enough that no more pairs could be born. At that point, the remaining particles should have found their opposites, destroyed each other, and left behind a universe that was vast, cold, and utterly empty of stuff. There would be no stars. There would be no planets. There would certainly be no one here to ask why. But as you sit here in the silence, the evidence of a lucky glitch is all around you. This is the deeper layer of our origin story. For a reason that still troubles the greatest minds in physics, the universe chose a side. At some point within that first second, a tiny, almost imperceptible imbalance emerged. The data shows that for every billion particles of antimatter that were created, there was 1,000,000,001 particles of matter. Consider the scale of that imbalance. It is a difference of 1 part in a billion. If you had 1,000,000,000 grains of white sand and 1,000,000,000 grains of black sand, and you removed just one single black grain, the difference would be invisible to your eyes. You would have to count every single grain, one by one, for years, just to find the missing one. Yet, that tiny, lucky imbalance is the only reason you exist tonight. As the universe cooled, and the Great War of the first second came to a close, the annihilation began in earnest. Trillions upon trillions of particles found their twins and vanished into light. But when the dust settled, that one extra particle in every billion had no twin left to fight. These survivors were the victors of a ruthless particulate battle. They are the particles that eventually formed the first atoms of hydrogen and helium, the first stars, and the 7 octillion atoms that make up your body right now. This is confirmed science. We know this battle happened because we can still see the shrapnel. The light released during that massive trillion-fold annihilation didn't just disappear. It has been travelling through space for 13.8 billion years, cooling down and stretching out as the universe expanded. Today, it is known as the cosmic microwave background, a faint, persistent hum of radio energy that fills every cubic inch of your room. For every single atom in your body, there are roughly 1 billion photons of this ancient light currently rushing through the void. You are the 1% of 1%. You are the leftover of a cosmic catastrophe. The existential weight of this fact is difficult to carry. We often feel like our lives are the result of a long, planned progression, from the Big Bang to the stars to the Earth to us. But the measured reality is far more fragile. We are the result of a broken symmetry, a tiny error in the mathematics of the beginning. If the laws of nature had been just slightly more perfect, if the symmetry between matter and antimatter had been absolute, the universe would be a graveyard of light. Scientists call the process that created this imbalance baryogenesis. We are still searching for the exact mechanism that caused it. Some experiments, like those performed by Chen-Ning Yang and Robert Mills, or the study of neutrinos in the frozen wastes of Antarctica, suggest that the weak nuclear force might be the culprit. This force, which governs radioactive decay, appears to treat matter and antimatter just slightly differently. It is as if the universe has a very slight preference for one hand over the other, a fundamental lopsidedness that allowed a few extra particles to slip through the net of destruction. But while the war of matter gave us the stuff of our world, it also left us with a disturbing mystery. By the end of the first second, the victors had claimed the field, but they were still just a hot, disorganised gas of protons and neutrons. They were the ingredients for a world, but they had no structure. They were like a pile of bricks sitting on a vacant lot, waiting for an architect. This leads us to the next complication in our investigation. If we only had the matter we can see, the stars and the planets, it wouldn't have been enough to build the universe we see tonight. Something else was there, hidden in the shadows, acting as a template for the first galaxies. As you lie here, moving at over 1 million miles per hour through a sea of ancient, annihilative light, consider the sheer improbability of your own atoms. Every carbon atom in your heart and every oxygen atom in your lungs is a veteran of that first second. You are not a spectator of this history. You are the physical proof that the war of matter ended in our favour. The victory was narrow. The imbalance was tiny. But it was enough. In the next chapter, we will look at the dark template, the invisible hand that took these surviving particles and pulled them together into the nurseries of the first stars. We will discover that the matter we can see is only a small fraction of the story. But for tonight, as you rest in the aftermath of a 14 billion-year-old victory, that is enough. In the previous chapters, we traced our history from the lawless bubbling of the quantum foam to the ruthless particulate battle of the first second. We saw how you, and everything you can touch, are the lucky survivors of a cosmic war that almost ended in a universe of pure, dead light. But as you lie here in the stillness, surrounded by the objects of your life, we must face a humbling partial resolution. Everything you have ever seen, the stars, the planets, the moon, and your own body, is merely the foam on top of a much deeper, much darker ocean. We now know that normal matter is only 5% of the universe. Think about that number for a moment. 5%. To understand what this means for your place in the cosmos, consider your own day. If your entire 24-hour day were represented by the matter in the universe, the stuff you can see, your home, your family, the sun and the distant galaxies, would account for only about 72 minutes. The other 22 hours and 48 seconds would be composed of something entirely different, something invisible, something that has been acting as a dark template for our existence since the very beginning. This is not speculation. This is the measured reality revealed by our most precise astronomical instruments. We are the 5% minority. We are the decorative trim on a building whose foundation and structure are made of materials we cannot see, cannot touch, and still do not fully understand. The investigation into this invisible force began not with a high-tech satellite, but with a quiet observation of the wrong speeds. In 1933, a Swiss astronomer named Fritz Zwicky was studying the Coma Cluster, a gargantuan collection of over 1,000 galaxies located 321 million light-years away. He was doing something similar to what you might do if you were watching a merry go round at a local park. If you see children spinning on a merry-go-round, you know that if it spins too fast, the children will be flung off by centrifugal force. The only thing keeping them in their seats is the strength of their grip. Zwicky applied this logic to the galaxies in the Coma Cluster. He measured how fast they were moving and how much visible mass, stars and gas, was there to provide the grip of gravity. The results didn't make sense. The galaxies were moving 10 times faster than they should have been. Based on the visible matter, the cluster should have flown apart millions of years ago. There wasn't enough stuff to hold it together. Zwicky proposed that there must be a vast amount of unseen mass lurking in the dark. He called it dunkel materie, dark matter. For decades, Zwicky's finding was treated as a curiosity, a potential error in measurement. But in the late 1970s, the mystery returned, this time through the work of the pioneering astronomer Vera Rubin. Rubin was studying the rotation of our neighbour, the Andromeda galaxy. At the time, she and her colleagues were working with cryptic punch card readouts from their instruments. But the story those cards told was unmistakable. In a normal system, like our solar system, the planets furthest from the Sun move the slowest. Neptune makes a stately, slow progression compared to the frantic orbit of Mercury. This is how gravity works. The further you are from the mass, the weaker the pull, and the slower you must move to stay in orbit. Rubin expected to see the same in Andromeda. She expected the stars at the very edge of the galaxy to be moving much slower than the stars near the bright central bulge. But the data showed something impossible. The stars at the outer edge were whipping around just as fast as the stars in the centre. Imagine watching an Olympic sprinter and a toddler running a race. You expect the sprinter to pull ahead instantly, but in Andromeda it was as if the toddler was keeping perfect pace with the sprinter, mile after mile. The only way this is possible, without violating the fundamental laws of motion, is if there is a massive amount of invisible mass providing extra gravity at the edges. Rubin calculated that the visible stars were only about 15% of the total mass. Every galaxy we have measured since then, including our own Milky Way, is cocooned in a much larger halo of invisible dark matter. This brings us to the invisible hand of the beginning. If we look back to the cosmic dark ages, the period after the first light was released but before the first stars ignited, the universe was a relatively smooth, cooling gas of hydrogen and helium. But as we discussed in the chapter on the First Symphony, there were tiny random shimmers of overdensity that had been seeded by quantum fluctuations. Normal matter, the baryons, was slow to react. It was still hot and prone to pushing back against gravity. But dark matter was different. Because it does not interact with light, it did not feel the outward push of radiation pressure. While the normal matter was still vibrating in the primordial symphony, the dark matter was already quietly clumping together. It acted as the template. It was the first to collapse into long, cosmos-spanning filaments and dense nodes. Imagine you are in a dark room where someone has laid out a series of invisible magnetic tracks on the floor. You cannot see the tracks, but if you scatter a handful of iron filings across the room, the filings will instantly snap into place, revealing the shape of the tracks underneath. Normal matter is the iron filings. Dark matter is the invisible track. By the time the universe was a few million years old, dark matter had already built the scaffolding of the cosmos. It created invisible gravity wells, nurseries for the stars, into which the normal hydrogen gas was sucked. Without this dark template, the hydrogen would have taken much longer to clump together. There would be fewer galaxies, less vigorous star formation, and potentially no planets or life today. You are sitting in your room tonight because 13 billion years ago, an invisible hand pulled the first atoms together into the specific nurseries where your ancestors, the stars, could be born. The question that remains, of course, is, what is it? Scientists are currently investigating two main candidates. The first are MACHOs, massive compact halo objects. These would be normal objects that are simply hard to see, like small black holes, cold neutron stars, or brown dwarfs, stars that never quite got big enough to ignite. However, as our telescopes improve, we find that there simply aren't enough of these objects to account for 85% of the missing mass. The second candidate, and the one currently favoured by most cosmologists, are WIMPs, weakly interacting massive particles. These would be a completely new kind of particle that sits outside the standard model we discussed in the last chapter. They would be ghostly particles that do not interact with light or electromagnetism at all. As you sit there, it is estimated that trillions of these WIMPs are streaming through your body every second. You feel nothing. They pass through the walls of your room, through the earth, and through you without leaving a trace, interacting with you only through the incredibly weak force of gravity. The existential weight of this realization is profound. We spend our lives focused on the 5%. We build our civilizations, our identities, and our dreams out of the shrapnel of the Big Bang. But we are living in a dark universe that is largely indifferent to our presence. If dark matter were to suddenly vanish tonight, the stars in the Milky Way would fly off into the void. The grip holding our galaxy together would fail. The universe is not just space and stars. It is a complex, invisible architecture of which we are merely the final decorative flourish. But there is one final piece to this puzzle. As we look at the balance of the universe, we find that dark matter and normal matter together only account for about 32% of the whole. There is another, even more mysterious force that is pushing the universe apart, even as the dark matter tries to pull it together. In the final chapter, we will look at this unfolding now. We will see how the universe is still beginning, and why the ultimate destiny of everything you see is to be diluted into a dark, expanding void. But for now, as you rest in the quiet of your room, consider the invisible hand that built the walls around you. You are part of an ancient hidden structure. You are the 5% that has learned to see the other 95%. And for tonight, as you drift in the shadows of the dark template, that is enough. Everything we have discussed so far, the lawless bubbling of the quantum foam, the violent stretching of inflation, and the first frozen symphony of sound, leads to a single, startling realization. The universe is still beginning. We often speak of the Big Bang as a historical event, a distant fire that happened 13.8 billion years ago. But the data shows that the bang is a process that has never stopped. As you lie here in the quiet of your room, you are not living in the aftermath of a creation. You are living inside the creation itself. Space is growing between us even as you listen to this. This is not a poetic metaphor for the passage of time, but a measured physical reality of our cosmos. Scientists have calculated the rate of this growth. For every 3.26 million light-years of distance, space expands by an additional 70 kilometers every single second. This means that the further away a galaxy is from you, the faster it is rushing into the dark. A galaxy located 326 million light-years away is receding at 7,000 kilometers per second. And those at the very edge of our vision are moving away from us faster than the speed of light. To understand this scale, we must humanize these astronomical numbers. Imagine you are standing on a giant, infinite rubber sheet. If you and a friend are standing close together, the sheet between you grows slowly. But if you are miles apart, there is much more sheet between you to expand. And so you appear to fly apart at a terrifying velocity. You are not moving through space away from each other. Space is simply being born between you. There is more space in the universe tonight than there was when you began listening to this investigation. This growth is driven by the most mysterious force in existence, dark energy. We now know that normal matter, the stars, the planets, and your own body, makes up less than 5% of everything that exists. The rest is a combination of dark matter and the even more dominant dark energy, which accounts for approximately 68% of the universe. While gravity tries to pull things together, dark energy acts as an intrinsic energy of empty space, pushing the walls of the cosmos outward at an ever-accelerating rate. For the entire history of our solar system, we have been living in an era dominated by this invisible expansion. You might feel like a spectator watching this vast dark machinery from the safety of your room, but the truth is far more intimate. You are a participant in this expansion. In the language of Einstein's relativity, every particle that makes up your body, every electron in your nerves, and every quark in your heart has its own world line. A world line is a path drawn through the 4 dimensions of space and time, tracing your journey from the past into the future. Think of your life as a bundle of these threads. Before you were conceived, the world lines of the atoms that now compose you were dispersed across the stars and the ancient gas clouds of the primordial soup. As you grew, those independent paths condensed into a tight, complex bundle, a knot in the fabric of space-time that you recognize as yourself. For a fleeting moment in the 14 billion year life of the cosmos, these world lines are bundled together. Eventually those threads will unravel and scatter back into the void, tracing new paths through the future universe. You are a brief knot in the fabric of eternity. This leads us to the final, most haunting possibility of our origin, the idea that the universe is a dream of a dead past, trying to understand itself through you. If we follow the logic of the information genesis, everything we see might be an illusion born of pure probability. In a universe that is truly infinite and eternal, even the most unlikely things must eventually happen. If you wait long enough, a 1 followed by 100 sextillion zeros of years, random fluctuations of energy could, by pure chance, form any shape imaginable. This means it is mathematically possible that our entire living universe is actually a pop-up universe, a brief, improbable glitch in a much older, dead cosmos that has already reached its final state of heat death. In this view, you might not be a real human being evolved from the Big Bang, but a Boltzmann brain, a disembodied consciousness that has fluctuated into existence with your complete set of knowledge and memories already intact. While this sounds like science fiction, it is an unavoidable consequence of our best theories of entropy and probability. You are the universe looking back at itself, wondering where it came from, even if the beginning was just a lucky arrangement of information in the dark. As we move into the next decade, our investigation into these mysteries will only deepen. New instruments, like the James Webb Space Telescope, are already looking back to the first 200 million years after the beginning, seeing galaxies that are far more structured than our current theories can explain. We are searching for primordial black holes that may have formed in the first second of time, and we are building detectors to listen for the sonic booms left by the first neutrinos. We are living in a golden era of astronomy where technology is finally catching up to our imagination, but for all our searching, we must accept that some mysteries might remain forever mysterious. We do not yet know why the constants of nature are so finely tuned to allow for life. We do not know what happened before the Planck War, or if the North Pole of time even exists. We are searching for a theory of everything that can bridge the gap between the tiny quantum world and the curving, heavy world of gravity. Until then, we are left with a partial resolution and an honest uncertainty. As you rest tonight, consider the velocity of your journey. You are moving at 1.4 million miles per hour through a current that was set in motion by a lucky glitch in the first second of existence. You are made of the victors of a ruthless particulate battle, and you are supported by an invisible template of dark matter that built the nurseries for your ancestor stars. You are a 14 billion year old experiment in self-awareness, suspended in a 93 billion light-year sphere of ancient moving light. The stillness of your room is an illusion. Beneath the silence, the fabric of space is still vibrating with the echoes of the first symphony. The beginning is not a point in the past. It is the very breath you are taking right now. We are the species that has learned to look at the other 95% of the universe and ask why. We are the bundle of world lines that has, for a brief moment, been granted the gift of sight. The investigation is ongoing, and we are the participants. But you have travelled far enough across the cosmos for one night. The paper has been folded 90 times, and the grain of salt has become the stars. You are safe in your windowless cabin, and the ship is sailing smoothly across the glassy sea of space-time. The North Pole is behind us. The stars are in their places. The dream continues. And for tonight, as you drift in the expanded quiet of a universe that is still finding its limits, that is enough.